Okay, so I will be recording this session and I've started the recording. Um, So we will start in a minute. Okay, so hello everyone. Welcome to Workshop on Computer System Security. And I am Nikita Yadav. I'm a PhD student in IIC Bangalore. I in the CSA department here. And about the workshop, so we had first day, like a day zero primary yesterday, and today we are starting the full workshop. And this is actually spread over the next 3 days, including today. And then on the day four, we will have a question and answer day. So the workshop will have it's like we will first look at the material, then after that we will look at some demos and quizzes related to the material. So if you want to know what topics are going to be covered, so you can check the schedule on the website, which is shown here. The link is shown here, and I've already sent this link to you via the emails. About me, I've already introduced myself that I'm a fourth year PhD student in the CSA department, and I'm working with Professor Vinod Ganpati in Computer System Security Lab. My broad area of research is system security, and particular, I'm currently looking at the attestation protocols. And if you're interested in knowing about my research work, then you can visit my website and look at the works that I have done. Now, the goal of this workshop is actually to introduce you to this field of system security. And the field is actually very broad because of like there are so many different domains where we can apply security, like web or like web is there, or say like satellites or blockchains, etc. So that's why the field is very broad, and it is impossible to cover the breadth of the field in this 3 day workshop. So, what we are actually going to focus in these 3 days are these topics related to memory vulnerabilities and exploits, such as buffer overflow and return oriented programming. And then we are also going to look at the defenses which have been proposed for these attacks. And on the last day of the workshop, we are going to delve into more advanced topics like trusted execution environments. In particular, we will look at the trusted hardware by ARM, which is ARM Trust Zone, and followed by we will look at a very important technique or mechanism, which is virtualization, which also provides isolation and of course is very important for security. So we will look at virtualization, and in particular we will also look at containers in closely, and then we will have a demo session related to the containers. I would like to make clarify that this workshop is not related to cryptography or privacy, and it is only related to system security. And I hope that will become more clear go as we go forward into the workshop. So the target audience for this workshop is anyone who is new to computer system security and who is interested in knowing about these different kind of attacks, defense techniques. And I hope that with the workshop, you will get a taste of system security. And then if you're interested, you can go and try new other courses and you can learn more. As I said, the area is broad, and of course, there is scope for learning new attacks, defenses, etc. So before I get started with the workshop, I would like to thank Professor Vinod Ganpati from IIC Bangalore and Professor Chester Ribeiro because I have from IT Madras, and I'm using the content in this workshop is adopted from their security courses that they have offered. So with that, let me go to the slides for introduction. Yeah, let's go to the introduction slides. Okay. Yeah, so there are so now we are going to get started. Uh, like before we get started with our actual content for this today, which is the attacks related to like memory vulnerabilities, attacks, and so on. I would just like to go over some basic terms in security, which will be useful for you as we go forward, and I think is required. So there are three basic like requirements or basic components when we talk about security. The first one is confidentiality. So what it means is that the data, which say it's secret data that must be kept uh, hidden, and the resources they must be kept hidden. For example, there are some secrets which can be, for example, any user data should not be available to the other users on the system. Or let's say you are using the encryption keys, the encryption is the encryption will be happening through some keys, so those keys also needs to be protected and the privacy must be there. So the first component is confidentiality. So when we talk about security, sometimes we are interested in confidentiality, but at other times we may not even care about confidentiality. And because the data that we are working with is not confidential in nature, and we may be interested in integrity. Integrity means that, so then there are these two different kind of integrity, data and origin integrity. And the word integrity means that the data is is in its original form basically. So if there is some data X, then the attacker is not able to modify that data. Okay, or if some computation is happening, then the attacker will not be able to modify that computation. And so integrity ensures that the data that we are working with, or any other party that we are working with, that party or the data is authenticated. It is as what was originally there, or it is the correct user. So then the integrity is also there. And apart from confidential and integrity, another important aspect is availability, which is like the attacker can also say, like you might have like think of it like that there is a resource like your server which is available, but the attacker can try to, like say, mount an attack on this server so that the server is no longer available to process the requests which are coming from the benign users. So these attacks and security attacks, they can try to uh, breach one of these three different aspects. Like confidentiality, the attacker can try to leak the secret keys or data which is there. It can try to tamper with the data which you are working with, or the computation that is happening on the device. Or it can it can impersonate some authentic user. And so the and finally it can try to disable the access to the data or the resources, so that that will also uh, hamper with the execution of your operations. So when we talk about security, then we might look at one of these three. Sometimes we may want only confidentiality, sometimes we may want only integrity, and the confidentiality is not important. So these are the three basic components, CIA. Okay, and yeah, and the goal of security is, first is prevention. So prevention means that you want to the prevent the attacker from violating the security policy that you have placed. And so when the defense is of a prevention type, then the attacker will not even able to do anything. But when the then the another type is detection. So the another goal can be detection. In this, the attacker will be able to violate the security policy, but the goal is to only detect this violation. So when we will be looking at in defenses, then we will be making this distinction that this kind of an attack is a prevention attack, and sorry, prevention defense, and it will be able to prevent the attack. Then there are some techniques which only detect the attack. The attack will happen, but then they will be able to detect it. And then once the attack has happened, then we should be able to stop it, and then we should be able to assess the damage that has been caused by the attack. Let's say, is it a leak of the encryption keys, or the data has been modified, or the computation output that we are getting is not, say, correct, and it is not reliable anymore. So, and then we should be able to recover the state of the system to the state before the attack happened, and so that the system can continue to function correctly even after the attack has happened. So that is recovery. And then very important is the threat model. Okay, so what is the threat model? Threat model term means that we will be describing that what are the assumptions that we are making in with respect to the attacker, like where the attacker can be. So your system, it has like so many components, as we were discussing yesterday also, that your system can have, say, these, you can think of your system as layers. Like there are applications running on your system, there is operating system, then there is your processor, and then of course you have a network facing, you can have a network facing interface, and where the other components or other external parties can communicate with your system. So there are these different layers in your computer system, and the adversary can be present on different layers. Like the adversary can be in the application, the attacker can be in the operating system, or it can be it can be in the hardware that you are using, or it can be a network adversary which is present somewhere else and is trying to send you some malicious inputs to your system. So in the threat model, we are basically going to define that where the attacker can be present, what are the powers of this attacker, like what resources can the attacker uh, basically say access. Like let's say if the attacker is present on the application in your computer system, then the attacker can only access the application memory by default. It can um, but if the attacker is present in your operating system, then the attacker can access the entire system memory. So we will, when we describe the attacker model or the threat model, then we tell all of these assumptions that where the attacker can be present. Then also we have to say the assumption that what part of the system is trusted. Let's say we can say, okay, we trust that the hardware is does not have any vulnerabilities, or is has not been tampered with. Or we can say that we trust that the operating system is secure and it is trusted, and we assume that there is no attack on OS, and therefore only the applications are in control of the adversary. So we have to define our threat model, basically saying where the attacker is present, what are the capabilities of this attacker, what it can do, and that is part of our threat model. And after this, and then we respect with respect to this threat model, then we will describe that what will be the concept of the secure system, but that will be with respect to this threat model. It's very important for us to first describe what is the threat model, and I've already given you examples of the threat model. Then there is this trusted computing base, which I've actually already described before earlier slide. So you can, when you in the threat model, usually we also write these assumptions that we make about the system, like which part of your computer system is actually trusted, which part of the computer system you are going to trust, like you are going to trust the OS, you're going to trust the hardware, and that part which is trusted is constitutes the trusted computing base or TCB of the system. And uh, and the assumption and what you are saying is that I am assuming that the TCB, let's say if it is OS, as long as the OS is not under attack, then whatever defense I am providing, that will work. Okay. But if the TCB is compromised, if say the operating system is compromised, then the defense that I'm proposing will no longer work, because for the defense to work, it's important that the TCB is uh, is is not under attack. Okay, so if the TCB is compromised, then we can no longer guarantee the security of the of the system. So what can be examples of the trusted computing base? Like I've said that we can say that the OS is trusted, or that we have a trusted hardware on the platform. Uh, and once we have this TCB, uh, then we can say, okay, this is trusted. And how low can you go on a real system? So you can put your trust as low as in the hardware. Like you can say, okay, I trust the hardware, such as we were going to talk about these trusted execution environments or trusted hardware. So we can say, okay, we trust the hardware, and as long as the hardware is not compromised, then the system will not be compromised. And then there are these two other things. One is the policy, and one is the mechanisms. So policies, what is a security policy? So the security policy is going to define that what is allowed on the system and what is not allowed on the system. Okay, so for example, it can define the security for your system, like say it is not allowed for a user to access the files of the other user. So that is a policy. Now, how do you enforce the policy? You do it with the help of mechanisms. So mechanism, like in real world, you can think of like the policy is that that outsider or stranger should not be allowed inside the home. And how do you enforce that policy? That is by putting locks on the doors. Okay. So when we are composing these policies, then it is important that the policies do not conflict with each other, and otherwise then discrepancies may lead to security vulnerabilities. Now, these were just some terminologies that we have looked at so far. And next, we are going to look at we are going to get started with memory attacks, buffer overflow, and other vulnerabilities. But before I start with that, I would like to say that um, I have disabled the permission for you to unmute yourself and ask questions. But if you have any questions, then you can leave them in the chat box, and then I will be taking those questions after a while. I will look at the chat box from time to time, and then we can see them. Okay, so there is a question regarding with I be sharing the recordings. The recordings will be available in the chat box. So then you will be able to see it. But okay, so now we are actually starting with the main content, which is we're going to look at buffer overflow attack, like stack smashing attacks now. And the buffer overflow vulnerability exists from like very, it's one of the earliest vulnerabilities in security, which was like found in the C programs, and it exists still today. And it has been exploited at various times, and it has with this it has like the recent most recent example is was a heartbleed, which was able to like leak the encryption keys. So the buffer overflow vulnerabilities exist even in the systems today, and they can be, and you will learn during the course now in next few hours that it is not that hard to mount. Okay, it is not very hard to do a buffer overflow exploit. And in the demo you will learn how to do it. And then of course there are some defenses which are in place to prevent the buffer overflow exploits, but they do not give any guarantees that it will not work. Okay, so they are not foolproof defenses as well, and we will also look at the defenses today. And also we will look at the demo for the defense. So what does come to your mind when you think, like when you hear this term buffer overflow? So the overflow, uh, of course, you it would mean that there is that something has been filled up beyond its capacity. For example, a dam. If the water is filled in the dam beyond its capacity, then the water will leak from the sides of the dam, and then it will uh, overflow the nearby regions. Now, when you think of this kind of a overflow in the dam analogy, then where do you think such a buffer, like similar to a dam, exists in your computer programs, in your C, let's say C++ programs? So where is this buffer space, which is holding some? So in the dam case, the buffer is the reservoir, and which is holding the resource is the water, which is holding the water. And when the water is filled beyond its capacity, then it will overflow. The same thing happens on a computer system also when you have a buffer overflow in your program. Now, where is this buffer located? So the buffer is actually the like a array. What is a buffer in your program? The buffer is actually nothing but a array. So when you allocate a array on your in your C program, and let's say you are writing to this array, then if you write beyond the capacity of this array, so let's say if you allocate if you define an array of size 20, and if you write beyond 20 integers, then you will be able to write beyond the capacity of the array, beyond the memory that has been allocated to the array. Now, what kind of a damage can this kind of a buffer overflow do? So this kind of a buffer overflow can, as I said, like it can be exploited to do very simply. It can be exploited to just crash your system, which we will see. It can be exploited to even run other programs, and it can be exploited to like say read other values in your system, like read other values in the process, such as the encryption keys. So So what is then a buffer overflow? A buffer overflow is nothing but a programming error. Okay. which happens in C and C++ programs and not in Java, because in Java at the runtime checks, it has a check that if you're trying to access an array beyond its capacity, then an exception is generated and you are not able to, and you will get a error like array index out of bound. But in C and C++, such checks are not there. So if you have allocated a buffer in your C program, then you can basically store the data in the buffer beyond its capacity, or you can read the buffer beyond its capacity. So now what we are going to learn next is how this simple programming error can be exploited by an attacker with simple programming, with simple engineering to launch a devastating security attack. So the buffer overflow exploits have a long history, and so the first buffer overflow vulnerability was exploited in 1988 by Morris, and this was the first computer worm, and it was called the Morris worm after Morris. And this was actually an accident. It was not intended to, he did not intend to do this attack basically. Then the next buffer overflow exploits has happened in 2001, 2004, Sasser worm, and then of course there were numerous, but the recent high profile incident was Heartbleed in 2014, by which the attackers were able to read the buffer beyond its capacity, and then they were able to read the encryption keys. And of course, once you have the encryption keys, then the data is no longer secret. So, so this buffer overflows have had this long history of exploits, and so I think it's very interesting to look at the buffer overflow vulnerability and the exploit. Now, what is the difference? Because I've been using this term vulnerability and exploit again and again. So what is a vulnerability and what is an exploit? So a vulnerability is like this programming error, which is or a bug which exists in your computer program, in your program. What is an exploit? An exploit is a step-by-step, uh, like it's a step-by-step some sequence that you will be carrying out to exploit, like to basically mount an attack using this vulnerability. Okay, so exploit is just a sequence of steps that you are going to use to do an attack on the vulnerability. So the further buffer overflow, let's to understand the buffer overflow problem, which I said is a programming error. Uh, let's look at this benign example. Okay, this example is benign. So here you have this function foo. Inside the function foo, you have defined a array, a character array buff of size 8, and so it can take 8. So you can store 8 characters here. Okay. Now what you're doing is here you're using the library function str copy, string copy, which is going to copy the source string to the destination's value, destination address. Okay, so this is the source and this is the destination. So it is going to take this string, which is null terminated, and it is going to store it here. Now, how copy works is that it is going to start copying from the first byte here, and it will copy until it sees a null character. Okay, so uh, so it will start. So that's why it will be copying HELLO, then space, then ORLD, and then it will see that there is a null, which is /0 null character, and when it sees a null character, then it will stop the copy. So although the buffer here, buff, is only of 8 bytes, it will be copying here these 12 bytes. The 5 bytes for hello, 5 for world, and then 2 more bytes, one for the space and one for the null character. So although the buffer you have allocated in the foo function is only of 8 bytes, the strcopy function, as you're passing it here, this string, which is of length greater than 8, but it doesn't check that what is the length of the source string, and it is going to copy it till it encounters a null character. So, but is this vulnerability exploitable? Uh, So, like currently, is this vulnerability exploitable? No, it is not, because here the string is of fixed length. Okay, you have already defined this string, so it is not exploitable. The attacker cannot do anything because the attacker cannot change the string. Hello world is getting stored. What might happen is that if you try to do this now, if you go and if you try to run this program, then probably your program will crash with a segmentation fault, and we will look why the segmentation fault occurs. But it is not exploitable by the attacker. So it is a benign buffer overflow vulnerability. Now, compared to the previous example, if we make a small change here, and if, let's say, in this function, it is a malicious example, here we have the function get user input. And we have this buffer, which is of size 1024. Okay, so there it is of size 1024 characters. And if we take the input from the user, okay, so it is reading the input from the user, and it will read until it will continue to read the user input until it encounters a null character, okay, on the command line. So the malicious user can run, can like give a very long input, which is the size for which is more than 1024 bytes. Okay, and what will happen is then this get s function is going to write the input which is coming from the command line into this buffer, and then it will be able to overwrite this buffer. Okay, so the program has allocated 1024 bytes for buffer. The getS function reads the user input from the command line, and then it writes into the buffer. And the getS will continue to read input until it encounters a null character. And potentially it will be writing more than 1024 bytes into buff. Now, still, I think it is not clear that why is it still a problem, like if you're writing beyond the buffer, but that will become more clear. Now, what this kind of an example gives here is flexibility to the attacker, basically. The last example on this slide, it didn't give the attacker any flexibility because the string was already fixed. Hello world. Only hello world is going to get copied. Here, the attacker has the flexibility to write anything into this buffer because the attacker can give the input to this program from the command line. So therefore, the attacker can write anything into this buffer and beyond the buffer. And we will see that how can that be exploited. Now, what can the buffer overflow attacks do? Why are they dangerous? So first, of course, is that they can write anything on the buffer. You can write anything in the buffer. You can write anything beyond the buffer. So you can basically corrupt the program memory, whatever is stored there. And when you corrupt the program memory, then it's likely that the program will crash because the program will no longer have the necessary data, the correct data in the memory. That is first. And that probably is not very interesting because you are able to crash this program. But what next? But the buffer overflow attacks have also been exploited. Sorry, buffer overflow vulnerabilities have also been exploited to hijack the program. But it means that they have been used by the attackers to start, like say, to create a shell. And once you have created a shell, then you can execute any code or you can access any files on the system with the privileges of the program. So when you start a program, let's say you started this program get input. So when you start this program here, let's say this is the program name is get input. And when you start this program, then this program is started with the permissions of the user. So if I am starting this program, it will be started on my machine with my permissions. That means that it can access all of the files, all of the resources for which the user has the access. So what happens is that if this program is hijacked, and if the attacker is able to create a shell inside this program by exploiting the buffer overflow vulnerability, the attacker will get the privileges of the program. It will get the privileges of the user who is running this program. And that is, of course, is very dangerous, because then the attacker can read all of my files. The attacker can execute any program, anything on my system. The attacker can say encrypt everything. The attacker can leak my data, send it over the network, or anything is possible. Then there is this particular kind of programs which are set UID root programs, set UID programs basically. Now, what are set UID programs? So set UID programs are these are special programs. Like examples of set UID programs are like sudo or password. These are command utilities on your Linux system. Now, what happens when you run a sudo command? So, when you run the sudo command, then temporarily your privileges are escalated from to a root user. Then you are able to do the root. You are able to do something which is only possible if you are a root user. So these programs are able to change the user ID. Okay, so like the sudo is able to change the user ID to the root user. And these are particularly dangerous if they are exploited with the buffer overflow vulnerabilities, because then the attacker can uh, change the privileges to the root user. And then basically it has access not only to the user who is running the program, but to anything else on the system. So so far I have only explained like what a buffer overflow vulnerability is, and what kind of attacks can be done using this buffer overflow vulnerabilities. It may not be clear right now, but it will become more clear as we proceed. Especially we will have we have demos both for crashing the program and then creating a shell. Okay. so So when you have this gettest program, that gettest based program, and if you give it a if you have a file with a very long content, okay, and if you're going to pass the content of that file to this program, okay, it is going to read the input from the command line. And if you're passing that long input to this program, then what will happen? What do you think that the program will do? So if you will run and check, so you will see that it will terminate with a segmentation fault. Okay, so now what is a segmentation fault? A segmentation fault happens when the program tries to access some memory which is not valid, some invalid memory location basically. Okay, so it will happen when the program is accessing some invalid memory location. And so, but why is that segmentation fault is happening here if you're writing the buffer beyond its capacity? Now, to understand that, we will have to understand the layout of the process, which we will come to in some time. But before with that, let's see that how can the attackers locate such buffer overflow vulnerabilities? Uh, So one of the techniques in security is called fuzzing or fuzz testing. So fuzz testing basically stands for the practice of feeding random inputs to a program and then observing its behavior. Okay, so it is like, even if you have this program and if it's like you're trying to first test this program, so what first testing means, you will give it random inputs. Okay, so you might give it an input of size 1, then an input of size 10, then 20, and you're just giving some random garbage bytes to this program. And the program will work fine until you give it, say, 1024 byte input. Might work even if you give 1028 bytes of input and so on, but there will come a time when this program will crash. Okay, so this type of a testing where you feed the program with random inputs so as to and then you observe the behavior of the program, that type of a testing is called fuzz testing, and it is used a lot to find security vulnerabilities. Okay, because uh, bec- it's also a testing mechanism, but it is also used to like find the security vulnerabilities. So if you observe that the program is crashed with a segmentation fault, then it is likely that the program contains a buffer overflow vulnerability. Now, that is the first step that an attacker would do uh, if they want to exploit the program, is like first test it and then find out if it has a buffer overflow vulnerabilities. And or some other vulnerabilities. And of course, there are other methods, like they can look at the source code. If the source code is available, they can, if the source code is not available, if the binary of the program is available, then they can do a reverse. They can look at the binary. They can try to uh, inspect the machine code. Now, to understand the buffer overflow attack working, we have to understand the process layout in the memory. Okay, so as you know that a program in execution state is called a process. Okay, that is what the operating system is going to create. The operating system takes the binary, which is like when you want to run a binary, then you are going to give this command on your command line, the dot slash binary, and then the binary is loaded into the memory, and then the OS will create a process. Now, if this is your program, which file that you have written, then this program file will have, say, program code, like the binary will have the binary code, machine code, and the data. And there are other sections or there are other segments, etc. And so when the process is created, when the binary, this is the binary, and when the OS is going to take this binary and run it, at that time, a process is created in the a process is created and the process image is stored in the main memory. So the global data is going to be stored in this particular location here, and the program code is copied here into this segment, text segment. Okay, and then you have also like the heap segment, where if your program is allocating any memory at runtime using, say, malloc, calloc functions, then that is allocated here. And then there is stack region. The stack region is what we are going to look at closely. So the stack is the region which is storing the local variables of a function. It is so for every function invocation, we create a stack frame. Okay, and that is a function activation. And the stack frame for a function contains the local variables of that function. The if that function is going to invoke any other function, then the parameters of the function are going to be pushed on the stack, and the return address, etc., are pushed. Then in every process memory, the kernel code and data is also mapped, and this is like useful when the program is trying to make a system call. So this is the memory representation of the process, and every process will have the same layout, and like it this is actually the virtual address space of this process. So within a process, all the data is stored as an array of bytes, and the C and C++ based programs, they allow the code to directly access the memory, okay, and they don't even check the bounds. Like we were seeing that you can write to this buffer or you can read from this buffer, and you can directly do that. But the bounds checking is not there. So you can read or write beyond the bound of the array. Hence, they are vulnerable to buffer overflow exploits. So again, I think this we have seen, but to check that everything is covered, every process has a address space in memory. Okay, this is the process address space. The address space is the set of memory addresses that are accessible to this process. So this process can access these memory addresses. Now, every address can store a piece of data, usually 1 byte long. So every address can store some data, and the computers, they understand the binary, and we represent these addresses as the hexadecimal numbers. So when we will be looking at the uh, program binary code, and when we will be doing the demos, then we will see that we are going to represent the memory addresses, these memory addresses, as the hexadecimal numbers. So for example, on a 32-bit processor, the address space of a process will range from all zeros in hexadecimal notation to all Fs. So this is the virtual address space of this process. And the all zeros is the bottom of the address space and all F is the top of the address space. So this is how the process is laid out from the top of the address space to the bottom of the address space. Now, if we look at it here, every program has this stack. As I said, every program has this stack region, and the stack region is actually dynamic in nature, means that it can grow and it can shrink. So the stack region will start from here and it will grow downward, and then it can shrink as well. Now, when you have multiple threads in your program, then each thread has its own stack region, and then they are placed at different locations here, okay, in this memory. But every thread will have its own stack. So when does the stack grow? The stack grows every time a function is called, and it shrinks every time a function is returned. Okay. So each function in the program gets an entry in the stack when the function is called. So if your main function is calling a function foo, then uh, a new stack frame is created for function foo. Now, when function foo has finished its execution and it returns, then that stack frame for function foo is destroyed, and then you return back to main. So that's how when the function is called, then the stack will grow, and when the function returns, then the stack is going to shrink. And the stack entry for a function reserves space for that function's local variables. And now we are going to look at an example and its stack. So let's look at the program here. It has two functions. One is main and another is foo. So the main function here is calling another function foo, and it is passing these three arguments, 1, 2, 3. And now this is here we have defined the foo function with these three integer arguments, int a, int b, int c. Okay, after that we have here defined two buffers, buff1, buff2 of size 8 and 12 bytes. Now let us suppose for the main function. And this is the bottom of the stack, and this is the top of the stack. Okay, so this is the bottom of the stack as we were looking in the last slide here. So this is actually here, it is reverse. So in the process address space, this is the bottom, this is the top, but in the stack, actually the above addresses, the addresses here are, that is the bottom of the stack, and the stack is going to grow downwards. The stack grows downwards. Okay, so this is going to be the bottom, this is going to be the top of the stack. And currently, the stack has only one entry, which is like the stack frame for main function. And on Intel x86, the stack grows downward, so the bottom and top are not where you would expect them. So as we move forward, you please take care of that. So the stack frame is actually, so there is something called a frame pointer. Okay, and in x86, this frame pointer is stored in this register EBP. Okay, the register EBP stores the frame pointer. So the what is the frame pointer? The frame pointer is pointing to the current, to the start address of the current stack frame. Okay, it is pointing to the start of the current stack frame. So currently the stack here, stack frame belongs to the main function. And the currently the EBP is at the bottom of the stack. And here, what is ESP? ESP is the stack pointer. So it is pointing to the top of the stack, and the top of the stack is stored in the register ESP. So these are two special registers, EBP and ESP. They denote the bottom of the current stack frame and the top of the current stack frame. Okay. Now suppose that we execute the statement where the main calls the function foo. So here main is calling the function foo, and let's say that this statement is executed. Now what will happen? So when main calls this function foo here, then it is going to push the so new stack entry is pushed to the top of the stack for the function foo, but several things happen before that. So it's like that before we are going to create a stack frame for this function foo, because we are calling the function foo. So whenever we call a new function, then we create a stack entry for that function. Now, but before we create a stack entry or a stack frame for this function foo, we have to do few things. Now, what are those things? The first is to push the arguments onto the stack. So first of all, the arguments of the function foo are pushed on the top of the stack, but they're pushed in the reverse order. So first 3 is pushed, then 2, and then 1. So they are pushed onto the stack in this order. Now notice that the value of ESP register, the value of the ESP here, which is the stack frame, it kept changing as the value of as the values of the function arguments are pushed onto the stack. Now, depending on the compiler that you are using, the arguments may be pushed by the main function or the foo function. So the instructions to push these arguments onto the stack, they can be either part of your main function or they can be part of your foo function. Here they are part of the main function, so they are being like here it seems that they are part of the main function, so they will be pushed onto the stack by the main function. Then okay, so now before we move forward, let's look at these instructions, like the assembly instructions that are there in x86, because we are saying that okay, they are going to push the arguments or etc. But these, it's important to know these instructions, and you may not have seen them before, so that's why there is this let's look at them before we move forward. And this also will come handy when we are looking at the demos for these attacks. So the push L push L sorry percentage EBP, this instruction is going to push the content of the EBP register onto the stack. Okay. So basically the push instruction is going to push the content of the register onto the stack. Here the register is EBP. The move L instruction here, where L is like the long. So L basically here will stand for like you are moving like 64 bytes. Like if there these registers are, sorry, 64-bit. If there's 64-bit register, then you're moving the content at 64. Like L is long. So you're going to move, the move instruction is going to move the current value of the ESP register into the EBP. So depending on the instruction set, it can differ that which of these operands is the destination or the source. Here, ESP is the source, EBP is the destination. So you're moving the content. Moving means you're going to copy the content of the ESP register to the EBP register. Okay. After that, we also have this subtract instruction. The subtract instruction is here, it is going to subtract value 4 in hexadecimal from the content of ESP. So then after this, ESP will have ESP minus 4 in hexadecimal. Okay. Then this instruction to call other functions is call instruction. It calls the function at the address this 0x80000470. This is actually the virtual address in the process address space. And so it is going to call this function. Now, when this instruction is executed, then the processor is also going to do, additionally, it is also going to push the return address onto the stack. Okay, so this is part of this instruction itself. Okay, the call instruction. The call instruction is going to do two things. First, it is going to push the return address on the stack, and then it is going to change the program counter to like change the flow of the program and it will start executing from this instruction, from the instruction located at this address. So now what is a return address when we're talking about in terms of these function? Now return address is the address of the next instruction. Okay, return address is the address of the next instruction after this call instruction. So if this call instruction is located at memory address X, then the return address will be X plus 1. I mean, not exactly X plus 1, but basically whatever is the address of the next instruction. That will depend on how long is the call instruction. So if the call instruction is 4 bytes here, then if the address of call instruction is X, then the address of the next instruction will be X plus 4. And the value X plus 4 will be pushed onto the stack. And then it will change the program counter and the function will start executing. Now here, this is move L. And here we have this like different kind of addressing mode here. Basically, it's a indexed addressing mode here, where you are going to store value like basically you're moving the value 1 into the memory, which is pointed to by EBP minus 4. So you're going to do this EBP plus, so it is actually EBP plus this value, but it's a but the 2's complement of this value is minus 4. So it's a minus operation, minus on the content of this register. And so this value is going to be, so 1 is going to be moved into the memory pointed to by EBP minus 4. Now, LEAL instruction loads the address of the memory location pointed to by EBP minus 4 into EAX. And finally, RET stands for the return instruction, and it is going to jump to the return address saved onto the stack. So when you to the call instruction, the return address is pushed onto the stack. And when the ret instruction is executed, then the content then that instruction is going to read the return address from the stack where it was stored, and it is going to change the program counter to this return address. Okay, so then the program will start executing from this location, which is pointed by return address. And NOP means that no operation. So these type of instruction means that do nothing. And so now we will look at the program again. And now here, let's say that the each argument is 4 bytes in length. And because the size of an integer in on Intel x86 32 machine is 4 bytes. So let's say that the each argument is 4 bytes. So ESP's value will be reduced by 12 bytes from when the function was called. Okay, so initially ESP was here, and then you push the value 3, then 2, and then 1. So every time ESP value was reduced by 4 bytes. So finally, the ESP has moved by 12 bytes down. Okay, so then when we will be looking at the demo, then we will look at the instructions which will be pushing the arguments to the stack, and then there will be other instructions also that we have already looked, like we will look at them in the demo. Now, afterwards, the code will, first of all, the main function is going to push the arguments onto the stack. After that, it will make the call instruction to the function foo. So when the call instruction is made to call the function foo, at that time, the ESP will be pushed down and the return address will be pushed onto the stack. Now you do not see this instruction explicitly in the assembly code. So as I was just saying, that it is part of the call instruction itself, that when the call instruction is executed, then the return address is pushed onto the stack. So after that, once you have pushed the return address, after that the processor starts executing the code into the function, will start executing the code into the function foo. But if you will look at the assembly code, then you'll see that the function prologue contains these instructions, which is the first is to push the content of the EBP register onto the stack. Okay, so the content of the EBP register will be pushed onto the stack, and after and why it is done? It is done to remember the location of the last stack frame. Okay. So this current value of EBP will be pushed onto the stack. When you do that, then the ESP will move forward. After this, the value of EBP will be changed to ESP. So then after this, the next instruction is going to change the value of EBP, make it equal to ESP. So both of these registers are currently, like the frame pointer and the stack pointer, are currently pointing to the top of the stack. And this is the previous value of the EBP. So now from here, the stack frame of the function foo will start. Okay, so the previous here so far was the stack frame of the function main, which would contain the local variables of function main. And if the function main is calling function foo here, the arguments to function foo, then return address after the call to function foo, and the value of the frame pointer. The value of the stack frame pointer for main function is pushed before the call to before the function foo starts executing. So this part is done inside the foo function prologue. And after that, once your foo function will start executing here, after that the instructions following would be to allocate memory for these two buffers, buff1 and buff2 onto the stack. Okay, so buffer1 is going to allocate, like for buffer1, like 8 bytes will be allocated, for buffer2, 12 bytes will be allocated. So, but the instructions, instruction following the subtract, like, so, but it is possible that the memory which is allocated for the buffer, it can be actually, although the buffer require only 20 bytes here, but the memory allocated can be, let's say, more. Like here, it could be possible that it is like it will be like subtract 0x20 comma ESP. So then the value of ESP register will be changed to ESP minus 32 bytes. So the stack frame is moved 32 bytes down. So that means 32 bytes have been allocated. Now this may happen, like this may be done for so as to align the buffer so that it becomes easier to like address the buffer, or this can be due to the optimizations that the compiler is doing. After that, so let's say that this is the buffer 1, which is 8 byte long, and this is the buffer 2, which is here allocated 12 byte long. So a new stack frame has been created, which is here shown by the yellow color, okay, for function foo. And this ESP now is pointing to the top of the stack, and EBP is now pointing to the stack frame of function foo. Now we have allocated these two buffers, buff1, buff2, of 8 bytes and 12 bytes, but totally in your memory, if you would, in your program, if you will see, it might have allocated, moved the ESP by, say, more bytes. Now, uh, Now, we have already discussed that we have pushed the value of EBP here, because so that when we return from this function, then we can restore the previous stack frame, the stack frame of the main function, because otherwise we would not know where is the stack frame for main started. Okay. So EBP always points to the bottom of the current stack entry, and the ESP always points to the top of the stack entry. And the return instruction, as we were discussing, it is going to, like there are these two instructions, leave and ret instruction, which are going to restore. The leave and ret instructions are going to, like, they are going to restore the stack frame to the previous stack entry. Okay. So they are going to, let's say, like change the ESP value again back here, so that these buffers are deallocated, and after that the EBP value will be restored to the previous EBP value, which is stored here. So the return, so as we have, so then so okay, so the EBP will be restored to the previous EBP value. So it will now point to here back when we have returning back from foo. And then we are going to use this return address, which is stored on the stack, to find out where to return in the main function. Because the foo function was called from main functions, and we had put here the return address, which is the address of the instruction after call to foo. And then when the foo function is returning, it is going to change the ESP, the value of the ESP register, it will restore the value of EBP register to the previous EBP. So it will now point here, and then it is going to use this return address. And these arguments will also be popped from the stack. So this will all get cleaned up. It will again point, ESP will again point to the stack frame of top of the stack frame of the main function. And the return address will be used to return to the next instruction in the main function. Now, so the return address which is stored on the stack, it's a very important aspect for ensuring the correct operation of a program. So if you tamper with the return address, then you can change the way the program's control flow goes. Okay. So if you change this return address, then the program flow will be changed, because then the program is using the return address which is stored onto the stack to determine where to start executing. Okay, so now we are going to look at a simple example, which is a benign example, to see that what will happen if you tamper with the return address which is stored onto the stack. And uh, when you will look at the assembly code of any function in any function, then you will see that the function will have in the end these two instructions, leave and read instructions. And as I just said, that leave and read instructions combined, they are going to restore, they're going to basically remove the they're going to restore the stack frame to the previous stack frame. So for that, they're going to change the value of EBP register, ESP register, and they're going to pop the value of the arguments. And now let's look at that here with an example. When the main function calls the foo function, the stack will look like this on the left hand side of which is shown here. And now when the foo function finishes its job and it is returning, then the stack needs to be restored to its original value, which was here, right? And moreover, the control needs to return from the foo function to the main function. So the leave instruction is in the foo function restores the value of EBP to the value saved onto the stack, and it pops the saved return value from the stack. So it is going to restore the value of EBP to the previous value which is stored into the stack here, and it is going to pop the return address which is also stored onto the stack. The read instruction changes the processor's control to the return address, which is stored onto the stack, and it pops the return address from the, so it pops the return value from the stack and it pops the return address from the stack. Okay, so it is going to uh, change the process control by changing the program counter to point to the return address, which is stored onto the stack, and then it is going to pop the return address. And when both of these instructions execute, then the stack is restored to its original state, that is this side. Now we will see here with the example shown here that how the return address modification can like what can happen basically if the return address on the stack is modified. So the code is as shown here. It's there are only two functions. First is the main function, and the main function has an integer x, and the value of the integer x is set to 0 in the beginning, and then it calls the function foo bar, and then after that x is changed to 1, and then when you printf the value of x. Now if you will compile this function, and you would expect the value of x to be printed here would be 1, because it is set to 1 here just before the printf function. But if you will compile, if you write this code, if you compile, then you will find out that the value of x which is printed here is not 1, it is 0 actually. Now, why is it 0? Like But if you remove this function called to foo bar from here, and if you rerun it again, then the value of x which is printed is 1. So, so something is happening inside this foo bar function, which is causing the printf to print value 0 of x instead of 1. Now, what is happening? So for that, we have to look at the foo bar function. Um But if we look at the foo bar function here, then we will see that we are passing it an integer argument. We're passing it literal 1. Then we are creating here a buffer of size 8, which is a character buffer. We have here ret, which is a pointer to an integer, and we are changing the value of ret. We are basically, setting the value of ret to buff plus 24, which is the address of the buffer plus 24. And so this now red has the address buff plus 24. And then we are saying that the value at the address stored in red, then change that value like plus equal 8, like change like add 8 to that value. Okay, that's what we are doing. And but we are not changing the value of x here anywhere. So if we are not changing the value of x, then how is it possible that when we run this function foobar, then printf is printing the value of x as 0 instead of 1, which is being set here. So if we will look at the stack for this, so as you can see here, so we have this x variable is set to 0, and x is a local variable in the main function. Okay, and we are then calling the foo function. So let us look at what the stack would look like when the main function calls the foo bar function. So here we have this, like say, the argument 1 is being passed, and then we push the return address onto the stack, and then we are pushing the value of the current EBP onto the stack, and then the EBP is changed to point here to the start of the foo function stack frame. After that, we have allocated a buffer as it was there into the code. We have allocated a buffer of size 8 bytes. And then after that, we have here created a local variable ret, which is an integer pointer. And then we have changed the value of ret to point to buff plus 24. And then we are doing something else. So here the stack entry for the main is shown in this green, and the stack entry for foo bar is shown in the yellow. And uh, if you will, so if for this to find out here exactly why 24 is being added, for that you actually will have to look at the assembly code of this program. But uh, so here, mm, but if you will look at the assembly code of this program, then you will find out that the EBP and the ESP registers, like initially when you allocate when you will, the ESP and EBP registers, when you will be, when the code, when the basically the code will be pointing here, when you will be, uh, when you are executing this code, and then when you are on this instruction, you will see that the ESP and the EBP are 24 bytes away. The value of the EBP is saved on the stack is 4 bytes. Okay. And the return address is therefore stored located on exactly 28 bytes away from the ESP. And the buffer is here. Okay, so I think yeah, so there are some of the details here are actually related to the assembly code of this particular function. But what is happening here is actually like say like the uh what is buff here? The buff is the starting address of this buffer. Okay, and you are adding 24 to the starting address of this buffer. So what will happen? So if this is buffer, so this is the starting address of the buffer, and it is saying here that the buffer is of 20 bytes. So if the buffer is of 20 bytes here, okay, then you are, this is the buffer, this is the buffer which is of 20 bytes here. And then there are 4 bytes for this value of EBP, which is stored here. So that makes 24 bytes. The buffer is 20 bytes, then 4 bytes for the EBP. So that together is 24 bytes. And what you are doing here is that you are taking the starting address of this buffer. You're adding 24, means you are moving, you have changed the address. Like you basically not changed the address so far. You have computed an address which is pointing to here, to the return address. Okay, so this is the start of the buffer here. You have added 24 to it. So 20 is the size of this buffer, 24, 20 is the size of this, 20 bytes is the size of this buffer, 4 bytes for this value of EBP, which is stored here. Then you have, so when you have buff plus 24 bytes, then you get the address pointing to the return address here, pointing to this entry, pointing to this location, which has stored the return address. Okay. Now after that, what you're doing is that you're saying, okay, now this is the address, and at this address, whatever is stored at this address, you add to that value plus 8. So if the return address, so basically it's going to do is that it is going to change this return address here. Okay, because it's a star, you're going to change the value at that address. First you computed the address of this location. Now you're going to, you're saying, okay, change the value at this address, that is the return address, and add 8 to it. So you're going to add value 8 to the return address. Now what will happen is, because of that is, so the next instruction in the program is, so now when your function foo is going to return, it is going to pick the return address from here. Now but the return address has been modified. Okay, and the next instruction in the program, which is going to be executed, it has been incremented. The pointer to the next instruction has been incremented by value 8. So this would cause the program to start from another location. So basically the instruction which is setting the value of x is equal to 1, that will be skipped because you have changed the return address. Okay. So here these are more details. So basically by incrementing the return address by 8 bytes, we are asking the processor to return to some another address, like say this 8048CD, instead of the original address, which was C5. And because of that, we will be able to effectively skip the instruction, which is setting the value of x is equal to 1. So we are actually not changing the value of x when we are inside the foo function. We are changing the address where the control is going to return. Okay, so we are actually just skipping the entire instruction itself, and so that that instruction will not get executed. And if that instruction is not executed, then the x value will remain 0, and after which, if you will print the value of x, it will still be 0. Now I will just go over it once more, because to very quickly, so that it is more clear. So here in the main function, we had this integer x, which was set to value 0. After that, you call the function foo bar. You're passing 1 as an argument, then you're setting the value of x is equal to 1, and then you're printing the value of x. Okay, so now here when you and in the foo bar function, you have created a buffer of size 8, and then you have a ret, which is an integer pointer, and the ret variable, in that you are computing some address starting from the buffer location, starting from the start. This is the start address of the buffer. You're adding value 24 to it. That would give you some address, and then you are changing the value at that address. You are basically incrementing the value at that address by 8. Now, this way, when we look at the functioning of this program, then we will see. So if you try to go and execute this program as it is on your machine, it might not work because you may have to modify this offset here. You'll have to look at the binary. You will have to look where what the size of the like basically you'll have to look at the binary. You will have to see how much space has your compiler given to allocated for the buffer. Here in this case, the assumption is that the compiler, not the assumption, but based on the binary for which this example like has been formed here. Here for this particular here in for this assembly code, the compiler has allocated 20 bytes for this buffer. Okay, so that's why 20 bytes, and plus then we will look at the stack layout. When we look at the stack layout, then we see that the next 4 bytes are used to store the previous value of the EBP. Okay, which is going to stay true. But you will have to figure out the size of this buffer, whether it is 20 bytes, 18 bytes, whatever the value has been allocated. Now, so you may have to change this value. Then you may have to change this value 8 also here, depending on if there are any other instructions just after the call. Sometimes there may be. So you may have to change the increment value as well. If you're trying this example, you can try, it will work, but you may have to change these offset values here. Okay. Now, looking at how this is working is that first of all, in your foo function, you are you have created a integer pointer. Okay, so the ret pointer, you are setting it to point. So let's say the ret pointer is initially pointing to the starting address of the buffer here, which is here. Then you are adding 20 to it. So then it will be moved here. And then you're adding +4 so that it is moved here. So ret is now pointing to the location where your return address is stored. Now you're saying that, okay, increment the value stored at the address pointed to by ret by 8. So this return address, which is stored here, which is the address of the instruction x is equal to 1, is changed. And so now you are going to skip that instruction, and you're going to directly go to the instruction which is printing the value of x. So you have skipped the instruction entirely, x is equal to 1. So on your control from foo bar is going to come back here, and that's why when you print this x value of x, it is printed 0. So this was example, and so this example may have convinced you that the it is important for us to like that the return addresses are important, like because if we are able to modify these return addresses, then we can alter the program control of the program. Like we were able to skip the instruction, and we can basically change the return address now to point anywhere else, okay, in the program. So what would happen if we let an attacker control the return address which is stored into the stack? What harm could it do? How could an attacker control the return address? So we will now look at that. Uh, but before we continue, I will stop here to take some questions, and we can, so let's stop here for a while and let's take some questions if there are any, and then we will continue. Okay, written. Okay, I'm sorry. Okay, sorry. Hmm. Okay, so there are questions on the chat. I should have looked through to take off. Is the segmentation fault only caused by buffer overflow? No, that is not true. Like, uh, that is not always true, but in this case, because you are, let's say you have not allocated a memory, but if you're trying to access, let's say you have not mallocked the memory for something, but you're trying to access it, then that also will cause a segmentation fault. So there can be other reasons for segmentation fault, but in this case, why the segmentation fault is going to happen, because you, when we have overrun, when we have written beyond the buffer, so as we just saw, we have modified these addresses which are stored on the stack, like the return address. So if you fill the return address with some garbage value, then when your program will try to return to that address will not even exist. And like it's likely that it will not exist. It's not a valid address, like some address which has been allocated. So it's going to cause a segmentation fault. It other way around, buffer overflow is a possibility if there is a segmentation fault. Segmentation fault is caused by if you try to access out of bounds. Yeah, so it is an indicator that the buffer overflow might be there, because in that particular example, get S, basically we have this program that is writing to the buffer. So when we give it beyond the capacity, then it is going to write out array, it is going to write beyond the array size. And that is what it is causing the segmentation fault. Mm, So if there is a segmentation fault, basically what we were saying in that when we do first test the system, and if there is a segmentation fault, when we are doing giving these random inputs, then there is a possibility that there is a buffer overflow. fault. Where are the pointers buffer1 and buffer2 stored? So the buffer1 and the buffer2 pointers, so I think that is the question is related to that we are not storing those values on the stack. Uh, so that information is actually maintained by the runtime. So in the it's in the symbol tables. No, it's a so this information is maintained by some other sections, like where are exactly these where are the pointers for? So this information will be like buffer1, buffer2. These are the local variables. The variables have been stored this memory onto the stack, and the symbol tables are not the symbol tables exactly, but there is some other information which is maintained which will contain that the local variables information, the addresses of these local variables. Is a new stack frame created for for function? So a new stack is not created for the foo function. We are basically creating a new stack frame. So the stack is same. It is just growing in size, basically, whenever we add more values to the stack. And so a new stack frame is created, but not a new stack. The stack is the same. That's just the memory allocated. There must be pointer variable, right? So yeah, that there must be pointer. I mean, that's not how it is actually maintained in the assembly. So you're going to, so in the assembly, the addresses of these buffers are like actually they are computed relative to the, like say the ESP, or so in your programmer's view, in your C program, you are accessing them with the buff1, buff2, etc. But when this program is converted to the machine code, then the compiler is doing all of this. The compiler is allocating say 8, so the size for the buffer1. Then if you are writing something to the buffer1, then the compiler has these instructions which are like compiler has changed this. So you are saying buffer1, you're saying buffer1 of 0 is something, then the compiler has those instructions. In the compiled code, you don't have the pointer to these buffers like buff1 or buff2, but instead there is this relative addressing. So you have the stack frame, you have the stack pointer or EBP, and with relative to these pointers in your machine code, these buffers will be accessed, and these buffers will be, say, changed or returned to. Also, allocation, whether variable happens in terms of pointer. Okay, I'm how it differentiates between the space allocated for different variables. Yeah, so as I was saying that is in your compiled code. Your compiler is generating this code, okay? So it is when you are creating the buffer, it is allocating. When the compiler is reading your high level code and converting it to the machine level code, at that time it is going to, this compile tool chain is going to like appropriately create those instructions which are going to, let's say, your know that where your buffer address is. Say your buffer is say located 20 bytes away from your start of the stack frame. So you will have a corresponding instruction into your machine code, which is like, okay, the stack is located at EBP minus 20, and so you have to start writing from here. But not a pointer per se is there in your machine code. The return address part is not, modification part is not clear for, I think it's regarding the latest example that we saw. When foo is called, next address is to execute x is equal to 1, but the called function modifies and make the ret address point to 8-bit next to the actual address which executes the printf. Yeah. Uh, I hope that this was clear. If not, I can go over the part again. And here the correction would be 8 bytes. So that 8 is 8 bytes. So, sorry. So in the foo, you are actually changing the return address, which is stored onto the stack, and you are modifying it basically by adding 8 bytes to it so that the next instruction, so that the return does not come back to x is equal to 1 statement, it comes to printf. Yeah, so how do you realize the size of the address like in the previous example you did? So yeah, that's a very valid question. So for this, as I was saying, that is depending on the assembly code. So when we will look at the assembly code, we will see these instructions. We will see that the compiler, we will look at the compiled code which is generated, and then we will see how much space the compiler has allocated for, say, this local variable buff. So in this case here, for the example that we were looking at, the compiler had allocated 20 bytes for the buff. So that's why 20 plus 4 because the value of EBP is also stored on the stack. So that makes it 24. So the buffer is located 24 bytes away from the return address. So that is why we have to get the address of the return address location, we have to add 24 bytes to buff. And during the demo session, I will show you this, and then we will look at some examples, and then we will also be computing these offsets based on those examples that we will be looking at. So then it will probably become more clear. But yeah, as you are saying, it's completely right. This 24 value is actually not fixed. Yeah, if you take that same program and you try to run it on your machine, it with this 24, it probably won't work because that is depending on the compiler, what the compiler code is generated. And you will have to look at the assembly code to find out the exact offset for this, and also the offset 8. Okay, so it is working with 24 on Linux with GCC. So then you tried this and you were able to skip the instruction x is equal to 1, and your program is now printing 0. So can you so you said that it is working with 24. So then probably others can also just, it's a very simple code, and you can all uh, actually, let me move back to the slides. Yeah. Why is it from beginning? Yeah, so uh, here we will actually pause for, let's say, 15 minutes. We will come back at 12 and restart. But before that, so during that time, you can take a break, or you can, I will let the screen shared so you can copy this program. You can try it on your machine. If it works, it's good. If it doesn't work, then the later we will see in the demo some other examples. We will actually look at the assembly and all. So then you can try to debug it afterwards. So let's take a break till around 12, and then we will come back. And I will continue with the lecture. Okay. Uh, I hope I'm audible, and I hope you had uh, like you were able to write that code and compile and see. And I hope that it was working and you were not the output that you were able to get was zero, and you skipped some instruction. You skipped the instruction as x is equal to 1. So if you were able to compile and if it was working, then you can tell, like you can say that you were able to do so in the chat box so that I know that it was working for you. And okay, so someone has a question. Okay. So we have seen that if the return address, so we have seen that the return addresses are placed on the stack frame. They're basically on the stack. And if we do not, and if these return addresses are corrupted, then it can modify the control flow of the program. And because of that, the you can say skip a instruction. And so that was one example, and of course that itself can do harm, but what more harm could it do? So that we are going to look at next. But let me first change the sites. Okay. So again, we are going to now we are going to say like consider this program here. Now you're calling foo function from the main function, and in the foo function you have this buffer of size 8 bytes, and in the foo function you're taking input from the user with the getS function, and the input from the user on the command line, it will read the user input from the command line until it sees a null character. Okay. And then it is going to write that value into the buffer. Okay. So if you we have just discussed some time ago that if you will give a arbitrarily long input to this program, then it will crash, right? Because then you would have rewritten the value of the return address with some garbage value. And it will happen because with getS, when you read the value from the stack, when you read the input from the stack, then it will start writing from the buffer starting address, which is here. And yeah, so we have to also, I think it was already clear to all of you, but here actually the stack is growing downward into the memory. So this is a larger address compared to this. Okay. So when the stack is going downwards means it is let's say this, if this address is 100, then this is say 90. This is then 90 minus 4, then 90 minus 8, etc. So it is growing downward. But when we are writing to the buffer, then it is actually incrementing. So that's why, of course, this is possible because we are writing. So when we start writing from the buffer start address, then we are going to write on the consecutive memory locations on over the stack. And then it is going to, if we write arbitrarily long, then we might overwrite the return address, thereby causing the program to crash. Um, so here getS allows an attacker to enter the data into the buffer. Since getS will keep writing into the buffer until it sees a null character, the attacker can keep writing into the buffer and possibly into other areas of the stack, including the return address, and then the attacker can use the input into the buffer to change the return address. Now, what address can this be changed to? That we have already seen that we can change it to skip a instruction. Now, let's try to write a exploit program. So For this, consider this simple program, which is actually invoking a shell. So to invoke a shell, you can use the execve library function call here, which is going to call the system call exec. And this is taking here these three arguments in this order, where where the first argument is the name of, is the string which is specifying the shell that you want to invoke. The second argument is this character array, which is which is a pointer to which is an array of character pointers, and where the first value is the this string, and then the second value is null, and the last argument here is null. So when you will run this program, then this program will create a shell. Okay, so shell means the command line. So if you will take this program and if you will compile it, and you will then get some assembly code which will look like this. Okay. So this is a call to execve, which is here. Okay. So execve is located at this address in your program address space. This is the uh, virtual address. Okay. So this is the address in your process address space. And like something like this call instruction is located at this address 800014E, and your execve function is located at this address. So the call instruction is going to change the control flow to start executing from here. But before the call instruction, we are going to push the arguments to the call. So that's what is doing it here. So it is pushing here uh, like, sorry, uh, wait a second, I'm not able to move the slides. Okay, so this is your program, okay, that you have written to start a shell. And if you will compile, then you will see. So in the main function, in the starting of the main function, as any other function, there is this function prologue. Prologue means this basically setting up the stack frame where you push the value of EBP, you move the value of EBP, you move the value of ESP into the EBP. After that, here you have subtracted 8 hexadecimal value, okay, which is 8 hexadecimal is 8 bytes. So here you are going to, one second, 8 bytes. So here it is hexadecimal 8, which you are going to subtract from the ESP. So that is you're doing to allocate this space for this name array that you are creating here. After that, you are moving the address into the EBP minus some value. And then after that, you're moving the value 0 into the this some address minus EBP. Okay, so this you are doing actually to fill the array. So here first you had created the array, right? Using this sub L, basically allocated space for this buffer. But after you have allocated the space for the buffer, then see you are using here the EBP, the frame pointer, as the and you're doing a relative addressing here. Okay, so relative addressing means EBP minus some value. You are using that to place the value, the address of the string. So this is the address of the string /bin/sh, which is being put into the uh, buffer that you have created here, which is located at EBP plus this value. And then you are moving value 0 into this address EBP plus this value. And so this will create this array. Then after that, you have to push the different values. So you have to, if you look at the arguments are name, say this array, right? This is also the array. And so this is actually the first argument of the array. And but that is a address, right? Address of this, and then the this is again the address of the this array, and then this is the null means. So then you're going to here push the arguments onto the stack. So you are now here pushing the value 0 onto the stack, that is null value. Then here you are computing the value of the like the next you have to compute the value, that is the compute the address of this array. So that you are doing here loading the address of that into the EAX register. Then you're pushing the EAX register here. Then you are again computing the address. So the address actually is going to be same here because the address of the array is same as the address of the first element of the array. They have the same addresses, so they are same. And then you're pushing that address, which is stored in EAX, onto the stack. After that, you're calling the function EX exact VE, and these are the arguments which you have already pushed. Okay, afterwards, when the call has finished and you will return back, then you will adjust the value of the ESP, move the, so basically what you're doing currently here, that you're now adding something to the ESP. So basically you are shrinking the stack now. Okay, when you have to grow the stack, then you subtract values from the ESP. So you move downwards, but now you're adding value here, C, which is like 12 bytes. So you are moving upwards into the stack. So, and after that, you are going to move the value of EBP into ESP. So then, or otherwise, I'm not sure which is the destination, which is the source here. After that, you are going to pop the value which is there onto the stack and then put it into the EBP. So that is like here you are restoring the stack frame. You are restoring the value of the previous EVP, previous stack pointer start, which was pushed onto the stack. Now you are reading that value, like popping that value and putting it into EVP register. And then you will return by reading the return address of the stack. So this is like if you will compile this, you generate the assembly, and it may look something like this. Okay, so this is a function, like this is the sequence of instructions which will be required if you want to say invoke a shell. Now the exec VE function will be called, and if you will then look at the exec VE function, then that will also have something like this assembly code. Now, if you will look at this assembly code, then you will see here, this is the interesting part here, which is int 80. So, so this exec VE library function call, it's a library function call, but the library function call is going to invoke the system call. Okay, and to invoke the system call, the instruction is this int 80, and this int 80 instruction is going to, uh, of course, it's also a function call. It will require some arguments that you have pushed onto the stack. You will push onto the stack. Okay, and then after that, the system call will execute, and the system call is going to start the shell because you have passed into your library function that you want to invoke the shell. So to invoke the shell, basically what you require is you require a null terminated /bin/sh string in memory. You need to have the address of the string in memory followed by null word. Okay, so you need to have in your program memory, this must exist. Okay, and then you need a null terminated this string, and then you need the address of the string. Once you have this, then you can like create like what you did here, you can copy these values, copy 0xb into EAX. Then that I this is not very clear to me, but you have to copy the address of the string into the different like you as if you were passing arguments. So when you are passing arguments, then you are actually you fill some registers for that. So you can copy the address. So like here, when you look at this basically when you look at this code here, for the for the system call, then you're passing the arguments here like this. You're pushing the some no, you're pushing this, but yeah, the arguments are here. Oh yeah, here. So you are passing the arguments with these registers actually. So you are actually in the next slide here, just trying to do the same. You're moving the 0xb value into AX. Then you're pushing the value of the address of the string into EBX, and the address of the string into ECX, then the address of the null long word into EDX. And after that, you are doing this instruction int 80. So basically doing this instruction sequence, if you have this instruction sequence, where of course these registers EBX, ECX contain the address of the string, uh, and the string and the this array, which the arguments which are required. Basically, if you set up these arguments correctly, if you're able to set up these arguments correctly, and then if you call int 80, then you will be able to invoke the shell. So that's it. And the basic requirement is that you need to have this null terminated /bin/sh string somewhere in your memory, and you need to find out the address of this string. And we will do this in the demos. We will find out the address of the string. We will find out the address of the system call, etc. And we will then put the correct arguments onto the stack. And once you have this, then you can create an attack payload. What does that mean is that you can like create this. Basically, you can then create this the sequence of assembly instructions which are calling the system call, which is like making a system call by executing this instruction. Before that, you have this sequence of instructions which are setting the arguments correctly. And then when you do this, then you can invoke the shell. Now, we have, say, created a payload. You may not understand it completely, but that is okay. But let's say that you have this payload, we're calling it an attack payload. And what this is doing here, it is just going to like make a system call, and then it is going to create a shell. Now we have this code, which is creating a shell. Now, where should we place this code into the process? Now, what we are trying to do here is using the buffer overflow vulnerability, we are trying to create a shell from the running process. Now, why shell? Because once you have a shell, then you can run any commands from that shell. Like you can list all the processes on the system, you can list all the files, you can read all the files, you can do pretty much anything with the privileges of the user who has started that process, to whom that process belongs to, right? So, so when you have this attack payload, okay, then you are going to convert that attack payload into the hex representation. Now, why the hex representation? Because this is the assembly code, and we cannot write the assembly code directly. We have to write the machine code. Okay, so you have to convert this hexa assembly code into this machine code. Okay, and then the machine code, let's say you place this machine code that you have generated, this hexadecimal representation of the code, and if you are going to push place this hexadecimal representation of the code. Let's say you put it into a character buffer. Okay. And then inside your main function, what you can do, if you try this, then you can create a pointer to an integer ret, and you have here ret is equal to int star address of ret uh, plus 2, and then you have int shell code. So you are here, uh, wait. So you have here, hmm, this is the address. You're placing this address here into the return value. So not the return value, basically. You're putting the address of this shell code into this uh, variable here, which is ret. And so if you will do this, then we have created the payload. I think so. The payload has been created in a such a way that if you will do this, then you will be able to like execute the shell. So the return address will be modified such that you will be able to jump back to the beginning of the shell code, and then this shell will be executed. Now this might not be, of course, this sequence or this particular code is not making very like how the exactly the return address is modified here. That is not very clear here, but we will see with an example later to actually correctly like how we can set up this return address and how we can move back. So what we are going to do is that we are going to write the shell code into the buffer which we were rewriting to, and then we are going to change the return address to point to the beginning of this shell code so that this shell code will start executing. And when this shell code will execute, then it is going to start the shell. And these are some like what it is saying is that in your attack payload, sometimes if you will say have any zero, like if you're doing say move zero value 0 to some value, and if you write this, then since this will be a null term, this will be treated as a null character. So your entire, if your attack payload, if it has say something like this, like a null string, null character, then if you create such a payload and if you try to write into the buffer, then of course you will not be able to write the entire payload to the buffer because it's null terminated. Like there will be a null character in between the payload. So in x86 gives you a lot of flexibility into rewriting such instructions so that you can avoid this the zero like values here. So you can rewrite the same instructions, like the same thing you can do in a different manner. Like first you can take these two registers, like first take the EX register, XOR it with itself. So when you XOR it with itself, then the EAX will contain the value 0. Now you can move the value of EAX into these registers, into these locations, pointed right by these registers. So then you have been able to avoid the values 0 into your assembly code and therefore in your payload. And so it will not cause the problem that your payload has a null character in the between. Like if it will have a null character, then it will not be able to run. So after this, again, like similarly, you can write other sequence, other instructions also into many other ways, because like they here, if you're moving, you have used move L instruction to move this value B into AX register, hexadecimal value B. Then since you are copying only one byte, so you can use the other instruction move B to do the same operation, and you can change the register from EAX to AL, the lower bytes of the lower part of the EAX register. And similarly, you can do this one. So the first instruction is used to move the value 1 into AAX register. The second instruction is used to move the value 0 into EBX register. Okay. So here what you can do is that first you can XOR the value of EBX register with itself. It will give value 0 in EBX. After that you can move the value of EBX to AAX, and then you can increment the value of EX. So it will give you the same result as this instruction. So it is like you have a lot of flexibility. Like, so basically so what it also shows is that there can be multiple ways in which the attack payload can be created. Okay, so there are like for creating the same kind of same for doing the same thing, like say invoking the shell, there can be different attack payloads because each can have different instructions. So far what we have seen is that the buffer overflow attack, which means that it happens because of a programming error when you are able to write beyond a buffer beyond its capacity. So because of that, what happens is that you may corrupt the other important uh, values which are stored on the stack, such as the frame pointer or the return address, and also other local variables or other variables into the other functions. So because you can write any much. So uh, because of that, so these, and you can also create a attack payload, and you can write that attack payload onto the stack, and then you will be able, you can change the return address to point to that attack payload, and you can execute that payload. Now, the attack, so that shows that the buffer overflow attacks, I mean, although we have not seen a demo, we will see the demo, but that shows that the buffer overflow attacks, what we have seen so far, that you, with the buffer overflow attack, you can say crash the program, you can skip instructions into the program, you can write a payload, like basically you can write another code sequence on your inside your buffer, and then you can change the return address to point to this code that you have written on the stack. And with this basically gives the attacker a lot of flexibility, and that is quite dangerous. So how do you defend from such buffer overflow attacks? So we have many like we have few techniques to do this. One is WXOX, then another is ASLR. And so we will look at these in details, but and about the return to libc attacks and the return oriented programming attacks, we will look at them in like we will look at them tomorrow. But today we are going to look at this WXOX and ASLR, and then stack canaries. So first of all, WXOX. So yeah, just to clarify, return to libc and return oriented programming, these are actually attacks which are um, not prevented basically even with something like WXOX or so that's why we it's like WXOX is defeated using return to libc attack, and then we have the return oriented programming attacks as well. So now first defense. Now we are talking about the defense for the buffer overflow attacks. Like how can we prevent the buffer overflow uh, attacks from happening? So the first one is that actually doesn't prevent all types of buffer overflow attacks, but it's like so in the last last like in the last what we have discussed so far was that we were creating this payload to invoke a shell, and then we are putting this attack payload onto the stack, right? And then we are changing the return address to execute this attack payload. Now, why is this possible? So this is possible because the stack memory is executable. And so you are executing something from the stack. But it is like not required, because what does stack contain? The stack contains only data of the program, like the local variables, arguments, return addresses, and so on. So the first technique to prevent not the buffer overflow, so buffer will get overflowed, but even if you have buffer overflowed, and if you write attack payload onto the stack, then you should not be able to execute it. So for that, we have non-executable stack, or the W XOR X. Now, what does W XOR X, or W XOR X specifies that the each page, so each like page in your process memory, that so there are some bits which are associated with them. So those are permission bits. So there are these three permission bits associated with the page in your memory, process memory, which is read, write, and execute. So these permission bits are saying that this page, let's say the stack page, uh, permission would be read and write. So that means that the stack pages can be read and returned to, but not executed. So the stack page cannot be executed. So the so there is this NX bit in every page table entry. Okay. And this NX bit is set into the pages which belong to the stack or the heap or the global data. So basically, any other segment in your program address space except the text segment, there this bit, non-execute bit, is set, which ensures that the attacker cannot arbitrarily write any code onto the stack and then execute it. Okay, so so, but this would still not prevent an attack, something like which we saw earlier, that if we are able to change the return address to say skip an instruction, right? We were able to change the return address in the example that you were trying, foobar, where you had changed the return address to point to the address of the printf instruction and skipping the instruction x is equal to 1. And tomorrow we will see that there are but in that attack, actually, you are only able to then say execute some code from your own program text section. So W XOR X here is giving you like it's basically preventing the attacker from adding any arbitrarily code into your program and then running it. Now, along with that, what does W XOR X stands for is that the it's a XOR, means if your page is writable, then it is not executable, and if your page is executable, then it is not writable. So, which means that the code pages, which are that is your text segment, that is only executable and not writable. So, your attacker cannot change the code pages, and your attacker cannot execute the stack or the heap or the data pages, basically. So this is giving you like this is basically preventing some class of buffer overflow attacks, which are which add the code onto the stack and tries to execute it. But it does not prevent, say, we will look at other class of attacks tomorrow, which is return to libc or return oriented attacks, and they are not prevented with the W or XOR X, and we will see that. Uh, now I will now we will look at the other kind of we will look at the other defense. Yeah, so now we will look at this other type of defense for preventing buffer overflow. Uh, The first, so here this is of course you can use a programming safe language such as Java to prevent the buffer overflows, but of course, still a lot of code bases are written in C and C++, including the operating system such as Linux. And of course, there is legacy C code. So we cannot uh, we cannot completely use choose always a safe programming languages like Java. And then the second thing is that to prevent it, you can do a black box testing. You can give it basically the first testing you can test it and on different inputs and different sizes of inputs and etc. You can first test it and you can check whether there are any crashes of the program, etc. or not. So then you can find out whether there are any buffers in your program or not. And of course, if you have the source code of the program, then you can check for these buffers. And if there are any buffers and if there are any functions which are like copying the content from some buffer, source buffer to the destination buffer without checking the size of the buffers. So that you can do. Other which we just discussed is that you can mark the stack as the non-executable section, and therefore the attacker will not be able to write any code onto the stack and then execute it. Then the next is randomize stack location or encrypt the return address on the stack by XORing with random string. So what you can do, and this is like ASLR, which is address space layout randomization, part of that, which is that you can randomize the stack location. So uh, why is the attacker currently able to, let's say, so when we looked at this attack sequences, you noted that we had to engineer these attacks. Like we had to know where the buffer was located. We had to know how many bytes away the buffer is located from, say, the start of the from the start of the stack frame, or how many bytes is it away from the return address. And so if the attacker has this information, then only the attacker will be able to change the return address in a very intelligent way, right? Or and now even when this return address has to be changed with some value, right? Like it has to be changed with the value, say, of some function that the attacker wants to execute. Now, if you randomize the stack location, and if you every time when the program is run, not just like for once, but every time when the program is run, let's say sometimes you allocate 20 bytes for the buffer, sometimes your compiler is allocating 30 bytes, sometimes 40 bytes, etc. So it is randomized every time the program is running, then the attacker will not know that exactly how far away is your say where exactly is the return address stored, or etc. Or what you can do is you can encrypt the return address, which is stored on the stack, by XORing it with some random string. And so then the attacker won't know what address to use in his string. Of course, these are not like foolproof techniques, but I'm saying here, like the randomize the stack location or these things. Of course, there will be attacks still possible here, because if the attacker is able to guess this correctly. And next is the runtime checking of array and buffer bounds. So we will look at one actually defense for this kind tomorrow. And that is actually a more foolproof defense, which is memory bound checking for these buffer overflow kind of attacks. But the other types like WXOR X, ASLR, and even the stack canaries, which we're going to look at in the next slide, they're not foolproof prevention mechanisms. Okay, so yeah, but if you do a runtime checking of the array or the buffer bounds, and if you at the runtime, like currently in C++ programs, this is not there, but if you are able to build a defense mechanism, which will check at the runtime that whether you're writing the buffer beyond its bound or not, then that can be used to, that of course will be able to prevent the buffer overflows. And this we have already discussed, that you can do analyze the source code to find out if there are any code or instructions or function calls which are copying the buffers without checking the bounds of the buffer, like the getIs function was copying the arguments from the user, like the sorry input from the user into the buffer without any checks, or the string copy is copying from the source buffer to the destination without checking how long is the source buffer or how long is the destination buffer. So for the runtime checking, actually there is something called stack canaries. We can put these canaries on the stack, and so the word actually canary was used for this was similar to like, actually this is like when people were used to work earlier into, they say, mines, and the mines would sometimes have, they say, some harmful gases or some poisonous gases, so that if people enter into these caves, then they might even die. So what they used to do was that they would use these small birds, canary. So they would put these, like send these birds into the caves, and these canaries, they would, like if they stop hearing the canaries voices, then they would know that there are some poisonous gases and they would not enter. So similar to that, like here we can embed these canaries, uh, like which is actually a random string onto the stack frame. And what we are going to do is that then we are going to verify the integrity of this canary before we return back. So what we are going to do is, like, basically your compiler is going to generate a stack canary, that is a random byte sequence, okay, which is stored somewhere in your actually globe, in some segment in your program. So this will be stored somewhere in your program segments, and this canary value is then placed on after the end of the buffer. So here the buffer is ending, and after that you are going to place the stack canary. So this canary is stored here on the stack, and it is also stored somewhere else in your program. Okay, so now if your buffer overflow attack is like say mounted, so what will happen, that the attacker will start writing the buffer from here, and it will start, when it wants to say write beyond the buffer size, then it will corrupt the canary as well. So to change the return address, because what you do, you have to write the bytes in sequence, right? You can't jump in between. So you will have to write, let's say from the starting of the buffer you're writing, and then you will, in the process to change the return address, you would have changed the canary as well. And now what your compiler is doing is that it has, so it's actually a compiler based defense mechanism. It's the compiler is doing this. It's by default, it is turned on GCC. And if you compile your program, and if you look at the assembly code, you will see code there for these canaries. So what your compiler is doing, it is creating this canary. It is going to place this canary at the end of this buffer. And if a buffer overflow happens, then that will damage the canary. And then when is it detected? So it is detected at the time of return. So at the time of the return, before returning to the function, before the return function return happens, it is going to take the value of the canary, like it knows that it has placed the canary here, and then it is going to check, like it is not necessarily placed just after the buffer, it can be placed say in the beginning of the stack frame or something. So it knows where it has placed the stack canary, and then it is going to take the value of this stack canary, and it is going to compare it against the value original value of the stack canary. And if it finds out that the it has been corrupted, then your compiler then it will throw an error. So the compiler has added these instructions so that the stack check fails, and then that function will be called, and then you will get a message on your system basically saying that the buffer overflow detected. So these stack canaries will be placed uh, into your, it is placed by, like it is a compiler defense, and you can enable the stack canaries. So with this, next, do I have something? Yeah, so as I just said, that the canary implementation requires you to compile the program again, basically, uh, because it's a compiler-based defense mechanism. The compiler is going to add these values, and the checking the canary integrity prior to every function return causes a performance penalty also, because you have added more instructions into the program. And like for example, it was 8% for Apache web server, but still I think it's not so it's not a very high penalty to pay. And so the however, the stack canary is defense also is not completely like foolproof. It has been defeated, and it has been shown that it can be defeated. Now, how exactly can it be defeated? I think it is something that you can uh, try to find out. Of course, this value is like, say, like any other randomized approach. If the attacker is able to learn the value of the stack canary, then the attacker can, if the attacker is able to know what is the value of the stack canary and where the canary is located on the stack frame, let's say by doing this, uh, by analyzing the program binary, then the attacker can change, like create a payload such that it will try to write in these bytes the exact same value as canary. Okay, and then this defense will not work. Okay, it will be uh, so you will be able to defeat the defense. So this has been shown that it has been able to uh, the defense has been defeated. So next is address space layout randomization, basically. So what does that mean? So you're in your process address space, you have these different segments, right? You have the code segment, data segment, heap segment, stack segment. So you can randomly, so ASLR is also by default enabled on all of the systems. Like if you now go and check, like which you can do, which I will show later, that how you can check whether ASLR is actually, say, enabled on your system or not. So so it is by default enabled. And what address space layout randomization does is that for every process address space, it is going to randomly choose the start address of these different segments, like the stack, heap, code segments. Further, what it does is that the stack frames which we were creating, it is going to randomly pad these stack frames. Like it is going to add, say, some padding before the stack frame is started. So you would not know exactly where, how far is the buffer start from. Okay, I think I lost my connection for just some while. I hope I'm back now. So the location, so the randomization can be done either at the compile time. The compiler can add these randomization like this stack padding before the stack frames. It can be done by rewriting the existing binary, so it can be done at the time of the linking, like at the link time or at the load time. Then it can decide that where to place these different segments, right? uh, so then, of course, it's still not a foolproof solution, because it's a randomization based solution. So it's a probabilistic solution. So if the attacker is able to, like, repeatedly, if the attacker tries to mount an attack, and if some point the attacker is able to say correctly guess the padding or something like that, then the attacker can still mount a attack even when ASLR is in place. So we have seen, like we saw what a buffer overflow vulnerability is, what a buffer, how can you exploit a buffer overflow vulnerability, what you can do with buffer overflow exploits. We looked at that to defend against the buffer overflow. There has been different strategies like making the stack non-executable, adding the stack canaries, randomizing the address space of the process. So these are the different defenses, and this is basically the uh, approaches which have been proposed to defend against the buffer overflow attack. Of course, tomorrow we will look at memory bound checking, which is also which will first tomorrow we will look at the other kinds of attack like return to libc and return oriented programming attacks, which will be able to defend against these which are basically which works even in the presence of these defenses. And then we will look at another defense mechanism called memory bound checking, which will be able to prevent any kind of buffer overflows in C programs. Now, I will stop here and I'll be taking some questions. We can take some questions, and after that, we can stop for lunch at 1 p.m. And then we will come back at 2. And when we come back at 2, I will start with the demos actually. Uh, if you want, then we can look. I think it's better when we start with the demo. So first we will look at GDB. So how we can use the debugger GDB to look at to like analyze the assembly code and the stack, look at the stack of the binary at runtime, etc. Then after that, we will look at how we can do crash the program, like why is the program basically crashing if we give it, say, this long buffer. And after that, we will create a shell using the buffer overflow exploit. So this will be the demos, and I have already put the demo codes actually on the GitHub. I will be sharing that with you, and then I will explain the demo during the demo how to do the attack, and then you can also try it out. And after the attacks, we have looked at these buffer overflow attack. Then we will look at the stack canary, how the stack canary is implemented by the compiler. We will look at those instructions and how can we enable ASLR, and we can check whether it's enabled or not, or how we can enable disable the W XOR X bits. So this is what we are going to do when we come back. Mostly it is only demos. If there will be time, then I might uh, look might teach after the demos are finished some other exploits, but mostly we will be focusing only on the demos. Okay, yeah, so yes, yeah, sure. During the demos, yes, I understand. I think it is not. I will try to make the demos. So I will try to do the demos actually in two ways. That first I will do the demo, and you can look at the demo more carefully. And then I will do basically I'll do the each demo twice. So first I will do it alone, and you can look at it more carefully. Then I will do it one step at a time so that you can also do it. if you are trying it out. And yes, I will try to stop more often during the demos to see if you have any questions, and we will try to make it more interactive. So if you have any question, then you can ask me now. Otherwise, we will stop the session here, and then we will come back at 2 p.m.